Bismillahirrahmanirrahim. In the last lecture, we have studied about the solving of differential equation. So we use the exact differential equation. We use the method of exact differential equation. And after that, we studied about the reducible to exact differential equation, in which we have studied already two rules. So third rule we are going to study today, which is in the given equation m dx plus ny n dy is equal to 0 if del m over del y minus del n over del x over capital N is a function of x only, that is x fx, say, then integrating factor is equal to e to the power integration fx dx. For example, x square plus y square plus x dx plus xy dy is equal to 0. So m is x square plus y square plus x and n is xy. Therefore, del m over del y is equal to 2y and del n over del x is equal to y. Hence, the equation is not exact, but del m over del y minus del n over del x over capital N is equal to 1 by x, which is purely function of x. Therefore, the integrating factor is equal to integration e to the power integration 1 by x dx. This is equal to e to the power log x, which is equal to x. Multiplying the given equation throughout by x, we get x cube plus y square x plus x square dx plus x square y dy, which is equal to 0, which is now exact. Therefore, the solution is integration x cube plus y square x plus x square dx plus integration 0 dy is equal to c, implies x to the power 4 by 4 plus y square x square over 2 plus x cube by 3, which is equal to c. This is the required solution of the given differential equation. Now rule 4. If the given equation is of the form x to the power alpha y to the power beta f1 xy dx plus x to the power alpha y to the power beta f2 xy dy is equal to 0, then we choose integrating factor x to the power h y to the power k, and then after the equations and then after the equation become exact, then we solve the equation for h and k, and finally we get the solution. For example, solve y cube minus 2x square y dx plus 2xy square minus of x cube dy is equal to 0. The given equation can be written as y square minus 2x square dx plus x 2y square minus x square dy is equal to 0, which is in the form x to the power alpha y to the power beta f1 dx plus x to the power alpha y to the power beta f2 dy is equal to 0. Now suppose integrating factor x to the power h y to the power k. Therefore, multiplying this integrating factor in the given equation, we get x to the power h y to the power k plus 3 minus 2 x to the power h minus 2 y to the power k plus 1 dx plus 2 x to the power h plus 1 y to the power k plus 2 minus of x to the power h plus 3 y to the power k dy is equal to 0. It is of the form m dx plus n dy, which is equal to 0, where m is equal to x to the power h y to the power k plus 3 minus 2 x to the power h minus 2 y to the power k plus 1, and capital N is equal to 2 x to the power h plus 1 y to the power k plus 2 minus x to the power h plus 3 y to the power k. Therefore, del m over del y is equal to k plus 3 x to the power h y to the power k plus 2 minus 2 k plus 1 x to the power h minus 2 y to the power k. Del n over del x is equal to 2 h plus 1 x to the power h y to the power k plus 2 minus h plus 3 x to the power h plus 2 y to the power k. For equation to be exact, del m over del y is equal to del n over del x. Comparing the coefficient of like terms, we get k plus 3 is equal to 2 plus 2 into h plus 1, and minus 2 k plus 1 is equal to minus of h plus 3. This implies h is equal to 1, k is equal to 1. Therefore, integrating factor is equal to x, y, and therefore the equation becomes x y to the power 4 minus 2 x cube y square dx plus 2 x square y cube minus 4 x to the power 4 y dy is equal to 0. The solution is integration x y to the power 4 minus 2 x cube y square dx plus 0 dy is equal to c. Implies x square y to the power 4 by 2 minus x4 y square by 2 is equal to c by 2. Implies x square y square into y square minus x square is equal to c1. After solving, we get the required solution of the given differential equation. Now the next rule, transformation to polar coordinates. Sometimes conversion from Cartesian to polar coordinates helps solve the differential equation easily. So in that time we will put x is equal to r cosine theta, y is equal to r sine theta. So x square plus y square is equal to r square, and y by x is equal to tan x. Therefore dx is equal to cosine of x dr minus r sine theta d theta. Dy is equal to sine theta dr plus r cosine theta d theta. Therefore x dy minus y dx is equal to r square d theta, and x dx plus y dy is equal to r dr. Now we are going to solve the problem as solve x dx plus y dy over x dy minus y dx is equal to under the root a square minus x square minus y square divided by x square plus y square. Solution. We will change these xy coordinates into the polar coordinates by substituting x is equal to r cos theta, y is equal to r sin theta. We get r dr over r square d theta is equal to under the root a square minus r square over r square, implies dr over under the root a square minus r square, which is equal to d theta, implies sine inverse r by a is equal to theta plus c, implies sine inverse under the root x square plus y square over a is equal to tan inverse y by x plus tan inverse y by x plus c. Now we have finished how to solve the differential equations. We are going to solve now the differential equation of first order and higher degree. If the differential equation is of first order and higher degree, then we denote dy by dx by p. Such equations are of the form f x y comma p is equal to 0, where p is equal to dy by dx, equation number 1. Now we can solve this type of differential equation If the given differential equation is of the type 1, then we can find the solution of this differential equation in various cases. Case first, equation solvable for P. The differential equation of first order and nth degree is of the form p to the power n plus q1 p to the power n minus 1 plus q2 p to the power n minus 2 up to qn is equal to 0, equation number 2, where q1, q2, qn are the function of x and y. Equation 2 can be factorized into n linear form factors as p minus f1, capital F1, p minus capital F2 up to p minus capital Fn is equal to 0, equation number 3, where f1, f2, fn are functions of x and y. Equation 3 is equivalent to p is equal to f1 xy, p is equal to f2 xy, p is equal to fn xy, equation number 4, each of which is a differential equation of first order and first degree. If the individual solution of the equations in 4 are f1 xy c1 is equal to 0, f2 xy c2 is equal to 0, and fn xy cn is equal to 0, then the general solution of the original equation 1 is given by the product of these solutions as f1 xy c1 into f2 xy c2 up to fn xy cn, which is equal to 0. So we are going to solve some problems related to this method, which is dy by dx whole cube minus 2x dy by dx whole square minus y square dy by dx whole square plus 2xy square dy is equal to 0. The given equation can be written as p square minus 2x p minus y square p plus 2xy square, which is equal to 0, where p is dy by dx. Now after factorizing we get p minus 2x p minus 2y square, this is equal to 0, implies p is equal to 0, p is equal to 2x, p is equal to y square, and the solution of these three differential equation will be p is equal to dy by dx is equal to 0, implies y is constant c, p is equal to dy by dx is equal to 2x is y is equal to x square plus c, and p is equal to dy by dx is equal to y square is 1 minus 1 by y is equal to x plus c, or xy plus cy plus 1 is equal to 0. Therefore the general solution of the given equation is y minus c, y minus c, y minus x square minus c, xy plus c y plus 1 is equal to 0. Now case 2, equation solvable for y. Let y be expressible as a function of x and p as y is equal to f xp. Question number 1. Differentiating it on both sides with respect to x, we get p is equal to phi xp dp over dx. Equation number 2. Equation 2 is a differential equation of first order in p and x and can be solved. Let its solution be f x p c is equal to 0. Now eliminating p in between 1 and 3, so as this will be 3, so as to get a relation between x and y. However, sometimes it is not possible to eliminate p between 1 and 3, and in that case equation 1 and 3 together represent the solution where p becomes the parameter. Is, for example, solve 1 plus p x minus y plus e to the power p is equal to 0, where p is equal to dy by dx. Solution: the equation is solvable for y as y is equal to 1 plus p into x plus e to the power p. Differentiating this equation with respect to x gives p is equal to 1 plus p plus x dp over dx plus e to the power p dp over dx, implies minus 1 is equal to x plus e to the power p dp over dx implies dx over dp plus x is equal to minus e to the power p, which is linear in x. So integrating factor is equal to e to the power integration dp is equal to e to the power p. Its solution is x e to the power p is equal to minus integration e to the power p e to the power p dp. dp implies x is equal to minus half e to the power p plus c e to the power minus of p. This is the required solution of the given differential equation. Now case third, equation solvable for x. In this case the given equation may be written as x is equal to fyp, equation number 1. Differentiating it with respect to y on both sides, we get dx over dy is equal to 1 by p is equal to phi y p dp over dy. Equation number 2. This is an equation of first order in p and y. Let its solution be f y p c is equal to 0. Equation number 3. Eliminating p between 1 and 3, we get the required solution. However, if the elimination is not possible or not convenient, then 1 and 3 together represents a solution where p is a parameter. Now we are going to solve an example, which is p cube minus 2xyp plus 4y square is equal to 0, where p is dy by dx. The given equation is solvable for x as x is equal to p square by 2y plus 2y divided by p. Equation number 1. Differentiating 1 on both sides, it with respect to y, we get 1 by p is equal to minus of p square by 2y square plus p by y dp over dy plus p by 2 by p minus 2y over p square dp over dy. After simplification, we get 2y square minus p cube p minus 2y dp over dy is equal to 0, implies 2y square is equal to p cube, 2y dp over dy is equal to p. 2y square is equal to p cube gives rise to singular solution. Hence for general solution we have 2 dp over p is equal to dy by y, which on integration gives 2 log p is equal to log y plus log c, or p is equal to under the root cy. Question number 2. Eliminating p between 1 and 2, we get x is equal to cy by 2y plus 2y by root cy is equal to c by 2 plus 2 root y over root c, or 16y is equal to c 2x minus c whole square, which is the required solution of the given differential equation.